Secondly, thank you very much, Chemtech Foundation, for giving me this opportunity to come and speak on this occasion. And Mr. Himant Shetty, thank you for those kind words. And Batraji, Suanshu, and panelists on this in this panel discussion, Mr. Pandey, Mr. Raja, and then you already have spoken, Ms. Batra, and all the delegates who are attending this conference. Now, as Mr. Pandey mentioned, corrosion is a big menace. It is it costs the world heavily, and as he mentioned, the cost of corrosion control is of the order of 3.5% of the GDP. Even in the countries like USA, which is developed countries, it is of the order of nearly 4.5%, and countries like us, which are developing countries, maybe it is even higher. And so it's an important subject. However much you put emphasis, it is insufficient. Number one. And then, wherever you go in your daily life, you see corrosion. It's a natural phenomenon in the nature. And whether you travel by bus, train, airplane, or ship, or you drive on the road, you see the advertisement hoardings, the bridges, the dams, and also the buildings that you live, or some of these places where it's only you can see the corrosion effect. So sometimes it's what I would say great eyesore to see the effect of corrosion. And so what is actually a corrosion? Because very specific to the project of today's discussion, I would subject to discussion today, I actually would like to just mention, and because to bring the subject to the context, what is corrosion? Corrosion of metal is a chemical or electrochemical process in which the surface of metals, the surface of surface atoms in the metal react with substance that comes in contact with the surface. So that's fundamentally the corrosion process. And usually the corroding media is liquid, or also the gas or the solids can also be corrodants. And then the electrochemical corrosion in metals in natural environments such as air, water, or even underground soil, it's caused by flow of electricity from one metal to another metal, or from one part of the metal surface to another part of the metal surface, as long as there is a condition for permitting electricity flow. So these are the two elements of the corrosion, which is very relevant for today's subject. And in the corrosion process, there are two reactions taking place: the oxidation and the reduction. The rate of oxidation and rate of reduction are equal. And so what you have an anode, you have a cathode, and in the anode, you have oxidation taking place, you have in the cathode, reduction taking place, and in a process, there is a continuity established, and the current flows through the electrolyte, which is either moisture, water, whatever medium. So you have now in the cathode end, there is a reduction reaction taking place, resulting in generally production of hydrogen. A very thin layer of hydrogen is formed on the cathode surface, which actually prevents the continuity of flow of the electricity now. Actually, the corrosion will stop at that. But unfortunately, it is not going to be so, because if there is oxygen present, then that oxygen reacts with hydrogen, that thin film is broken, the electricity, the continuity is reestablished, corrosion continues, oxidation process continues, reduction process continues. Point of the matter I'm actually trying to stress is, so all of these are happening at the surface of the metal. So it's important, if you want to now control that corrosion and eliminate or mitigate or reduce, you need to treat and handle that surface. And that is exactly what is meant by either a surface treatment or surface engineering. Now, I would be not doing my duty if I did not cover the erosion part along with corrosion, because surface engineering also involves tackling the erosion problem. And exactly the same way, the metal surface engineering involves mitigation or addressal of the erosion. So how do you do? So there are many ways of modifying the surface of a metal which is generally subject to corrosion and avoid and in order to avoid corrosion, if you have to modify, how do you do? For example, if I were to take gears or a compressor blade or a turbine blade, all these are, if you have a very high speed pump and where the tip speed of the impeller is so large, so these are the very susceptible parts of an equipment where it comes in contact with abrasive or erosive material. So there will be erosion problem. And it is more enhanced, more pronounced if that particle which is coming in contact is corrosive as well as erosive. So what do you do for erosion? Tackling erosion, you have to harden the surface. Take the example, as I mentioned, either harden the surface or do a coating depending on the temperature of operation, as long as the coating stands. So how do you do the hardening of the surface? There are many methods. These are all as part of the surface engineering. You do flame hardening or diffusion heat treatment like carburization or nitriding, or a laser or electron beam hardening by spraying, applying very high energy. And also there's a process called short peening to improve the fatigue properties. You stress this element, and so you improve the fatigue properties. So these are some of the ways in which you can tackle the erosion problem. Coming to the corrosion part of it, as steel is a common metal that we use for simple reason that it has got strength, it has got ductability, it has got ease of fabrication, it has got dent resistance, and it's got every possible properties that you're looking for. At the same time, it is inexpensive, and unfortunately, it is susceptible to heavy corrosion. So how do we do that? So again, we come to the topic of surface engineering of metals to avoid corrosion, and you have several processes because, as I mentioned earlier in the opening remark, you need to treat the surface, you need to engineer the surface. So there are many methods of engineering the surface, and for example, alloying the metal itself. Take for example steel itself. So alloying with chromium, nickel, and superior material. By doing that, the corrosion properties of metal will be much improved, means it will be reduced. You have hot dip galvanizing, which is a very normal, the process that everybody is used to. You see the galvanized sheets, galvanized steel, etc. And then you have the aluminizing, and you have also anodizing. The titanium. People think the titanium doesn't corrode. It does corrode if it is subject to very high acidic, like acetic acid medium. Titanium corrodes. So you need to do anodizing to treat or engineer that surface. Electroplating, like you have chrome plating or nickel plating, thermal spraying, then vapor deposition technique for very hard coating. And unfortunately, with the higher temperature and higher pressure, the problem becomes more severe. So you need to tackle the process with probably higher expensive process. You'll have to adopt. So depending on the cost means when I say it's a life cycle cost. So initial cost plus operating cost for maintenance, and you take into account also the size restrictions. For galvanizing, for example, the galvanizing tank size limits the size of the material that you can galvanize. So you also have other constraints like the technical properties itself. So you require, for example, the distortion tendency of the material. So you cannot, if you have to deal with that, so you need to apply a certain process that you're then taking care of that as well. These are the general processes that are available as part of for surface engineering. As Mr. Pandey and Mr. Batra and you people said, there is innovative things coming into the market, and I'm sure it's a continuous process. More and more better processes will come, and the people who are in the business, like coating, the painting, and the alloy people, they're alloy, like with the boron doping, it gives tremendous properties enhancement. But coming to very specifically to refining or petrochemicals industry where I come from, all this is okay for external protection, etc. We have a serious problem in dealing with the equipment and material. Example, cooling water system, where we have cooling water circulating in the heat exchangers, very common piece of equipment. And if the corrosion is not controlled there, it'll lead to downtime unexpectedly without knowing even. So it's a serious issue. Exactly the same way in the boiler. And if you are not managing the boiler's surface engineering, so again, a corrosion will set in there, and it's a very dangerous thing. How do we do this? So in case of cooling water system, because you have oxygen present there in the cooling water, water is there, and because the oxygen is in the form of dissolved oxygen, and so it's always a corrosive atmosphere prevailing there. And there, what is the primary requirement is to actually form a thin protective layer and protect the basic surface of the metal so that it is not attacked. And in order to achieve that, you have effective cooling water treatment programs, and these actually involve phosphate treatment. And that again, it's not that calcium phosphate or magnesium phosphate layer is formed purposely, and which protects the attack from the corrosive medium prevailing in the cooling water. But at the same time, you have to be clear at what level you maintain that calcium phosphate in the cooling water circulating system. And it cannot be too much. If it is too much, then you have a problem of deposition and scaling. Scaling means it affects the heat transfer coefficient. And if it is too less, then in the case of eddies or thermal shock or anything untoward happening in the system, and that layer will get away. And the moment layer goes away, that thin protective layer, and so you will have the corrosion set in. So what we need to have is excessive phosphate quantity in the cooling water system, but maintained in a dispersion form. And so you need to provide some dispersant and to make sure that you have the phosphate quantity. Phosphate is generally maintained through trisodium. There are several phosphate we use, including the phosphonates. And with that, the phosphate level is maintained so that you neither have scaling problem nor the corrosion. Now, most important part in this is if you are leaving, when we start off this treatment program or commission the heat exchangers without taking care of preparing the surface, then it will be a disastrous result. And I can guarantee you. So that is why before you even launch a program, you need to ensure that the metal surface, the virgin original metal surface, is in absolutely clean conditions. That means no oil or grease, no rust or mill scales. So there is what is called a passivating process. You clean the water, you clean the surface with surfactants to remove the oil and grease. You clean with acid, by doing acid cleaning, pickling, etc. And then you deposit in a controlled manner but calcium phosphate and magnesium phosphate or iron phosphate on the cooling water system. That part of the commissioning is the key to a successful treatment program and to ensure that that surface is maintained in proper condition and the corrosion is avoided in future during operation. Coming to the boiler, in a cooling water system, you can say that you do this because there is always oxygen. In boiler, inside the boiler, what do? You actually work to remove the oxygen content in the boiler feed water, because for the corrosion, most important factors are you need to have metal surface, you need to have air or oxygen, which is required for making sure that there is a reaction taking place in the cathode. So you have water, air, and continuity. So in case of cooling water, we make sure that there is a film formed and it is protected. In the boiler water, what do you do? So typically in a boiler feed water, you deaerate the water, remove the dissolved oxygen totally to, I think, 2 to 4 ppb, parts per billion. So the impact of oxygen is much reduced. Again, in preparation for the boiler to have a proper corrosion control, we need to have, before we do the commissioning, make sure that there is proper alkali cleaning and surfactant cleaning to remove the oil and grease. You do acid cleaning, and then when you're commissioning, you're actually commission and form a magnetite hard deposit or a film. It's not a rust magnetite, which is one form, is a partially oxidized product, which is hard. Fully oxidized product is nothing but ferric oxide, which is rust. So we do not want rust to be formed. So you need a hard magnetite film formed, and that is what you do by proper treatment during the commissioning, and make sure that magnetite layer is maintained during the operation, and that maintenance is done by typically disodium or trisodium phosphate or mixture of that and a particular pH level, and ensure that it is maintained at a certain level so that it is the water doesn't get into become basic or acidic, and it's typically maintain that pH of the boiler water inside the boiler around 9, so that they are not corrosive. And this is typically in petrochemical and refinery industries, where you have an environment which may contain sulfur dioxide, nitrous oxide, and all kinds of impurities, etc. But if you go to a power plant, typically there is no such problem, and the water is absolutely pure. And as long as the water is very pure, you can actually manage with all volatile treatment, such as amine. And but there is no hard magnetite layer formed in those treatment programs. So these are some of the possible, I would say, as a metallurgist talks about hardening and alloying, and also the coating people talk about painting, coating, and all that. As you said, polyurethane coating, epoxy coating, and all that. But when it comes to the process industries, then we need to actually handle it in a different manner. And these are also part of the surface engineering. With that, I actually, because this is a subject which, we can talk for hours and days, and every subject in the surface engineering, every sub-subject is a vast technical issue, technology involved, and a lot of innovation taking place continuously. And with that, I wish the 2 days program a grand success, and I also wish the participants will benefit from these proceedings and will have something to take home at the end of these conference proceedings. With that, thank you very much again, Chemtech Foundation, for giving me this opportunity. Probably I exceeded the time, and I didn't make note of the time when I started. Sorry about it. Thank you.